Oh, yeah,
Hey
it should be
guys.
recording.
Okay, great. Hey guys, welcome. Today we'll have a guest appearance, a special guest. Well, it's Jack. He's gonna show us two Putnam problems. All right, Jack, it's up to you right now. Go
All
for
right.
it.
So the very first problem we're going to be going over is Putnam 2001 A6. So let's see. In this problem, we have a parabola intersects a disk of radius 1. And we're asked if we can find the arc length of the parabola in the disk to see if it ever exceeds 4. So can the arc length of the parabola ever exceed 4? So let's go ahead and start off by drawing a few diagrams to get an idea of what we're looking with. So right here, let's just draw our plane. And since the parabola and the disk aren't given, we can just move them in an optimal way that makes the problem easier. So I'm going to go ahead and put the circle here. I'm going to put it right here on the origin, right? With this being 0, 0 here. Can you see that little circle
Yeah,
thing?
yeah.
Yeah?
Well, it doesn't look like a circle to me, but anyway.
Yeah. It's supposed to be a circle.
Yeah.
If you
Anyway,
think
it's a
hard
circle.
enough, it might be a circle. But, and then for our parabola, oh, that's another circle again. Got to turn that off. For our parabola, it's going to look something like this, right? Because it's got to be inside this circle. So basically, we're asked if this red parabola here, if its arc length will ever exceed 1. So some important things that we should try to figure out, sorry, not exceed 1, exceed 4. Some important points that we're going to need to know are these ones, up here, this point right here, and this one here. That way we know where exactly our parabola is actually intersecting the circle. Because the idea is going to be we're going to take an integral, which represents our arc length of this parabola. So we're going to need to know this point here. So we can get this x value and this x value here. That way we can integrate and use our basic Cal 2 integrals to try to see if we can come up with something useful. So let's first start off by getting those points. So the circle, its equation is just x squared plus y minus 1 squared, because remember, this is a disk of radius 1, so that means the circle centers right here at the point over 0, up 1, and that's exactly this equation here. So we have our equation for the circle, we just need the one for our parabola, and our parabola is going to be y equals ax squared. So this a right here is a variable, which is going to determine what our parabola looks like. And we don't need any of the extra terms that you would normally have, like the x term and the constant, because we've constructed our parabola in such a way that it'll not have those and just fit in the circle nice and neatly like this. So all we're concerned with is this one variable a, and we have to see if we can find some a that makes this parabola have an arc length exceeding 4. So a few things to note about a right off the bat is we know a has to be positive, because if a was negative, then our parabola would be going down like this. It would be down here, right? And we can't have that because it has to be up inside the circle, because if it was pointing down, it wouldn't even be in the circle at all. So we know that a has to be greater than 0. And that's the only limiting factor we know on a. So let's go ahead and try to find these 2 green points. And by doing that, we're just going to solve this system of equations right here. We just have to plug in our parabola into the y value for the circle. So let's go ahead and do that. Let's see. Oh, oops. I scrolled down too far. Okay. There we go. Let's go ahead and just crunch these 2 equations together. So we have x squared plus y minus 1 squared equals 1. And we know what y is. Y here is just a times x squared. So we have x squared plus ax squared minus 1 squared equals 1. And now we just have to solve for x. Nothing too difficult here yet. So let's just square this whole thing out. So that would be plus a squared x to the 4th minus 2 ax squared plus 1 equals 1. So let's just organize up a bit. Let's see what we have here. We have a squared x to the 4th. Let's see. We have 2x squared terms here, so we will get plus 1 minus 2a x squared. And then, of course, these 2 1s, those will cancel out, and we're just left with 0. So here we have this, and this is pretty nice. We can evaluate this quite easily. All we got to do is let's factor out an x squared. So we have x squared. So we're left with a squared x squared plus 1 minus 2a equals 0. So this is pretty good. Let's see. So now we're going to look at these 2 separate factors in this equation. Here we have x squared equals 0. And we have that a squared x squared plus 1 minus 2a has to equal 0. And this first equation here, that just means that x has to equal 0, right? And that should make sense because we, in fact, do have another point. I didn't label it, but I can. It's this one right here. So that's where our x equals 0 point comes in. We don't need it, but there it is. And let's go ahead and solve this second equation. This one should give us the 2 green points that we're actually looking for. So we can just go x squared equals 2a minus 1. Oh, sorry, a squared, x squared equals that. So that means x squared equals 2a minus 1 all over a squared. And then all that's left is to take the square root on both sides. And then remember, when you take the square root like this, you have to consider both the positive and negative case. So we have plus or minus the square root of 2a minus 1 over a squared. And then, of course, that's just plus or minus the square root of 2a minus 1 over a. And that looks good because we have our 2 green points. We have the positive one right here on the right, and then our negative one over here on the left. So we have our 2 green points, so we can maybe try to set up some integrals to evaluate the arc length of this parabola. So let's go ahead and call this green point right here, let's call that x naught. And so x naught, as we've seen down here, right, this is going to be x naught here. X naught equals the square root of 2a minus 1 over a. And we don't need the negative version because if you notice, a parabola here is going to be an even function. So getting the arc length of the whole thing isn't necessary. We just need the arc length of one of these branches here, and then we just have to double it. So that makes our actual integral easier to compute because we don't have two of these. We only have one of them, and then the other will be 0. So let's go ahead and actually set up our integral for the arc length of that parabola. So let's call whatever that arc length is, let's call it L. So L, of course, is the arc length of that parabola, and that's nothing more, if you remember back to Cal, I think it's 2, I believe. You get the arc length formula, so we're going to go, oh, sorry. We're going to need 2 of these. I just said that. We're going to need 2 times the integral of 0 to x naught. Remember, x naught being this point that we found here, this x value. And we're going to take the square root of 1 plus y prime squared, where y prime is the derivative of the function we're trying to find the arc length of, and with respect to x.
Yeah.
So this is just
y is y of x, right?
Yeah, y of x. Yeah.
Maybe you should write it y prime of x.
All right.
It's more clear. It's clearer then.
So we'll have y prime of x dx, where y of x equals ax squared, right? Where y of x is our parabola.
Yeah, so, it's y prime squared there, right?
Oh, yes, sorry.
Okay.
Yeah. So now let's just go ahead and see how far we can go in evaluating this integral. So we'll have 2 times the integral of 0 to x naught of the square root of 1 plus, and let's see what this is, right? So y prime of x, that's just going to be 2ax, right? And then, of course, if we square this whole thing, y prime of x squared is just going to be 2ax squared, with it, which is nothing more than 4a squared x squared. So let's just put that right here. 4a squared x squared dx. So now we're stuck with this complicated looking integral, and it can be evaluated. What you do is you do a trigonometric substitution, just like you would do in Cal 2. There's nothing too difficult about it, but just a bit of computation. Now, the problem is once we get it in that form, it's sort of hard to see what we can do next after that. So it's sort of a dead end. We're going to want to see if we can come up with some sort of trick to maybe find L in a different way. We still want to use this integral, but we want to see if we can manipulate it in such a way that makes it a bit easier so we don't have to worry about all of this trigonometric substitution. So the very first thing let's do, let's introduce a substitution that just sort of cleans this up a bit. So we're going to go ahead and let u be equal to 2 times ax. That would mean du is equal to 2a dx. And let's go ahead and do the substitution over here in our integral. So we have 2 times the integral of, we've got to change our bounds here. So when we plug in 0 for x over here into our equation for u, we get 2 times a times 0, which of course is just 0. And then when we do the same thing with x naught, we get 2ax naught. And then let's go ahead and work with our square root over here. We'll have 1 plus, and if you notice this right here, 4a squared x squared, that's exactly u squared. So we just are left with u squared, and then du, which equals 2a dx. That means that dx equals du over 2a. So we have du over 2a. And then let's clean this up a bit. These 2's here, they'll cancel out with each other, and we'll take this a and put it out front. So we're left with 1 over a times integral of 0 2ax naught 1 plus u squared du. Now, this is basically the same problem we had earlier, right? We can't exactly evaluate this integral in a nice fashion that'll allow us to prop up some inequalities. So we're still going to have to come up with something, but at least this looks slightly nicer. So let's go ahead and take a closer look at this right here, because we want to see if we can do something to this that will, maybe we can change it in such a way, maybe not keep it exactly, but put in something very similar to that, that allows us to do the integral far easier than it's written right now. So let's just take a moment to just think about what this function actually is. So let's go ahead and call this function right here, let's call it, I don't know, let's call it g. So g of, sorry, not g of x, is going to be g of u. G of u equals the square root of 1 plus u squared. Oh, that's out of range. There we go. Okay, so we're just going to let g of u be the integrand right here, and we're going to see if we can come up with any sort of nice substitution here. So let's go ahead and look at this function a bit. So, there we go. All right. That thing's a little annoying. I don't know if you can see it.
Yeah, I see it.
Oh, okay. Okay, there we go.
At
So we
least you
have
can draw
our,
straight lines.
what?
At least you can draw straight lines, not like me. Like my lines are
Oh,
like,
yeah. Yeah, I just found this out. I think it was like last night I was looking at it. It's like, oh, that's convenient. So let's look at this function right here. If you happen to know it, it's a hyperbola, just one branch of a hyperbola. And if you look at it, it's going to be, right, if we have g of u squared equals 1 plus u squared, therefore we have that g over u over, so we have that g u squared minus u squared equals 1. And of course, this is just the equation for a hyperbola. So that's what we actually have here, just the positive branch, right? So let's look at our hyperbola here. That's not a straight line. Let's look at our hyperbola here. Right, and if you remember back to like pre-cal and all of that, one of the key parts about a hyperbola are these two asymptotes. And this, of course, being the parent hyperbola, the one where there's no extra transformations on it. These asymptotes are nothing more than y equals x and y equals negative x. And then our blue radical right here, our hyperbola, is going to look something similar to this, right? It's going to asymptotically approach these two red lines. Oops, that's not a very good hyperbola. There we go. That's a bit better. There we go. So it's going to look something like this. Now, this is quite good for us because if we look at what we have here, our L, which is the arc length of our original parabola, we tried to maybe evaluate the integral, but it's going to be too difficult to actually come up with anything useful out of. So we want to instead take this hyperbola, which is sitting right here, the square root, and we're going to want to substitute in a different function, right? Because if we substitute in a function that always is less than our blue hyperbola, that means when we take the integral of that function, we're going to get a number that is less, right? So we'll end up getting something like, because we have L equals the integral of this right here, du, and instead we're going to substitute in something smaller. Let's call this smaller thing h of u, right? So if we substitute in something smaller, some sort of h of u, then of course, oh, sorry, that's not. If we substitute in something smaller, then this integral right here will also be smaller. That means that this function's arc length is going to be smaller, right? Because if this integral happens to be equal to 4, then we have that L is greater than equal to 4 for some a value. And we are done with the problem, right? We found the a value, and it turns out that it's true. Or it could come out to the fact that no such a value ever exists, but just sort of looking at the problem, there's probably going to be an a value. So we have to try to find it, and our best hope of finding that is finding some sort of h of u, some sort of function here that's less than this radical, less than this blue function here at all points. That way we can set up this inequality and show that L is always greater than or equal to 4 for a certain a. So that's what we need to show. So we need to try to find this h of u. That's our current goal right now. Now, there's a few pretty good candidates. I've written one right here on the screen right now, and that's this asymptote, right? Because it's always less than the function. It's its asymptote. It's never going to reach it. So maybe a good guess would be to try to plug in the asymptote as this h of u function. Because as we know, our blue function right here, our hyperbola, the square root of 1 plus u squared is always going to be greater than or equal to u, right? Where, here, let me do that u in a different color to match with our graph, right? Or u, right? Because we have right here our red asymptote and then our blue hyperbola. This blue function is always going to be greater, so maybe we could try substituting in u, and let's see where that gets us. So let's go ahead and try that. So we have that L equals the integral, it equals 1 over the integral from 0 to 2a x naught of 1 plus u squared du. And then we're going to go ahead and use this inequality here in our integral. And we'll get that this arc length here, this whole thing, is greater than or equal to 1 over a times the integral from 0 to 2a x naught u du. Now, this is far simpler than what we had before, and it's something we can actually evaluate right now. And let's go ahead and do that. So we have 1 over a times 1/2 u squared, and then our bounds from 0 to 2a x naught. And let's evaluate our bounds. We'll get 1 over 2a times 1/2. And then we'll have 2a x naught squared minus 0 squared. And let's just go ahead and do this algebra right here. We'll get 1 over 2a times 4a squared x naught squared. And then we'll have 2a x naught squared. So now with this right here, we know what x naught is. If you recall back to earlier, we said x naught was exactly this point here. We found it here. It's just the square root of 2a minus 1 all over a. So let's go ahead and put in x naught, right? So we'll have this equals 2a times the square root of 2a minus 1 over a squared. And that'll leave us with 2a times 2a minus 1 over a squared. And then we'll get, let's see, we'll have a 2 up here, 2 times a minus 1, and then of course this a will cancel with this a squared, and we're just left with an a on the denominator. And let's go ahead and maybe try to rewrite this in a better form that'll allow us to analyze what's actually going on here. So if we distribute this 2, we'll have 4a minus 2 over a, and then we'll get 4 minus 2 over a. Now, looking at this, I see an immediate problem with our inequality that we introduced. This isn't equal to 4 and it's not greater than 4. It's actually less than 4, right? Because remember, what is a? A is any positive real number. So a is any positive real number. Therefore, negative 2 over a is a negative number, right? That means this 4 minus 2a is going to be less than 4. Now that's a problem because if you remember back to our goal with this inequality here was to find some sort of function, h of u, that either evaluated out to 4 or evaluated out to something that's bigger than 4.
So u is not a good candidate.
Yeah, it was too small. And if you look at our original diagram here, we can see why, right? If we were to look at this, look at all of this extra bit here, right? This is too much. So we need to choose something that hugs our blue curve much tighter. So what exactly could that be? We know as of right now that we need a function that is going to be less than our hyperbola, right? It needs to be less than this. So our h of u needs to be less, but it needs to be greater than u because u was too small. That was too far. We need to find something in the middle. So my next process of going, how could we ever hope to find something like this, is it would be this function right here, right, our u, but we're going to add plus a little extra. We're going to add a little extra, right? So we need to find this little extra, and that will be our new h of u. So we need to find some sort of extra bit that will allow us to actually do this inequality so we get something that's greater than 4, not less than 4. So we know let's look back over here, at small values of x, right? Because if we take this asymptote and we're just going to add some other function to it, we know at small values of x, it needs to be fairly large. I mean, not really big. It doesn't need to be 10, but it needs to be bigger than what it would be at larger values. Because you can see over here, as x gets larger and larger, all we really need is the asymptote. All we really need is u. Our main problem comes from these smaller x in the beginning. So we need to find a function that is large at the beginning, but as it tends off to infinity, it basically goes away. So that's what we're thinking of when I say when I say the little extra bit. So the little extra bit will be some sort of function where at the beginning it's larger, and then as it tends to infinity, it becomes 0. Now, a great candidate for such a function that does that would be a rational function, right? So maybe we could try something like this function here. So if we were to try this one that did something like this, right? So as x gets bigger, it basically becomes 0. And here at smaller values of x's, we have a substantial sum to u. We're adding quite a bit extra, right? Whereas over here, we're basically adding nothing. And that's exactly what we're looking for. So maybe a function that looks like this will be beneficial. Now, what function is this right here? Well, the one I've just drawn is 1 over u plus 1, right? Because maybe the more obvious choice would be 1 over u when you think of rational functions, but there's one glaring issue with this. This function isn't defined at 0, and we're trying to take the integral at 0, right? So that's not going to work. We need to do something that's defined at 0, or else we're going to mess this whole thing up. So that's why I chose this function right here, this 1 over u plus 1, because at 0, this function just evaluates out to be 1, right? And maybe let's look at if this is
wait, u is positive, right?
yes, yeah. for
Okay.
positive u.
Mm-hmm.
So let's look at this and see if this is even a choice that would be less than our original hyperbola. Oops, that's an eraser. Right here, right? So is this statement even true? Is 1 plus u squared greater than or equal to, let's see, u plus 1 over u plus 1? Is this even true? Because if it's not true, well, then there's no point in doing this because we're trying to find a function that's less, right? If this right here turns out to be greater, well, I don't know what we're doing, but we're not solving the problem with that. So we need to check to make sure that this is true. And let's just evaluate out some cases for u. Let's start with u equals 1. Because if it isn't even true for u equals 1, we can hardly hope it to be true for all u. So with u equals 1, 1 plus u squared is nothing more than the square root of 2, which is approximately 1.4.1. And then u plus 1 over u plus 1 is equal to 1 plus 1/2, which is equal to 1.5. Okay. Well, so that means that this is false, right?
Yeah, I wanted to say that from the beginning. That's a little bit too.
Yeah, it's a bit too big, right? But it has the right idea in mind. So maybe we could make this little extra bit here, maybe a bit smaller, but we want it to have the same general idea. So let's just multiply it by 1/2, because that'll make it smaller.
Yeah, exactly. So
right?
instead of 1 over u plus 1, maybe you can put 1 over 2 times u
Yeah.
plus 1, right?
Yeah. So that would be the next thing to try, right? Because this is too big. But it has the right idea. So maybe let's see if we can, if this statement is true. U squared plus 1. Oh, sorry, I've been doing that the other way around. Let me be consistent. 1 plus u squared less than or equal to u plus 1 over 2u plus 1. Okay, now is this a true statement? Right? We have to prove it, because if we don't prove it, well, then we're not doing math, right? So let's go ahead and try to figure out if this is true. So let's take the right side here. Let's take u plus 1 over 2 times u plus 1. And let's go ahead and square that whole thing. It might seem a little weird to square it, but if you think about it, here on the right, on the left side, we have a square root. So if we're squaring both sides, then we're trying to compare it to 1 plus u squared, which is far easier to work with than having a radical over it. So this will just make for easier comparisons. So let's just evaluate this out, right? We'll have u squared plus 2u over 2u plus 1, right? Yep. And then our last term will be 1 over 4 times u plus 1 squared. All right, now let's just go ahead and try to consolidate this and see what we have. So we'll have a u squared here. And then let's put these two into one fraction. So let's get a common denominator. Over here we'll need 2u, an extra u plus 1, right? And we're going to need another 2, right? Because here we have a 4, so we're going to need another 2 and another u plus 1. That's going to be all over 4 u plus 1 squared. Yep. All right, now let's go ahead and continue with this. Oh, sorry, that's a plus. We'll have, let's see, 4u squared over 4u plus 1. Yeah. Yep. And then on the bottom, we'll have 4u squared plus 8u plus 4. Okay, so right here in this form, we can already see something's happening, right? Because remember back to our hyperbola here. We have a 1 and we have a u squared. We have a u squared, and then we have this fraction right here. And if we look at this fraction, as it turns out, this the numerator is actually going to be smaller than the denominator, right? Because these are the same. This one's bigger than this is bigger than this. So this whole function, right, this whole fraction right here is always going to be less than 1. So we have u squared plus 1. And then, of course, taking the square root of both sides, back up to our beginning, we have u plus 1 over 2. U plus 1 is going to be less than, from our inequality here, the square root of u squared plus 1. And that's just equal to 1 plus u squared. And we have exactly what we wanted, right? We wanted this. We wanted that our hyperbola is greater than this function here, and that's what we found. So now we can actually try to substituting this in, just like we did with the asymptote, and see if that gets us anything good. So let's go ahead and try to do that, right? So remember back to way back when we had our integral still on the board, it was 1 over a from 0 to 2a x naught 1 plus u squared du. And then using this inequality that we just found, we're going to substitute in this function right here into our integral instead of using our hyperbola. So let's go ahead and put that in. So that means that this whole integral right here, this L, our arc length, is going to be greater than, well, it's just going to be greater than, right? It's going to be greater than 1 over a times the integral of 0 to 2a x naught, and subbing in our new function, u plus 1 over 2u plus 1 du. Okay, now this is, again, a fairly easy integral to compute, so let's go ahead and do that. We have 1 over a, and then this right here, again, is just going to be 1/2 u squared, and then this one right here will be 1/2 times the log of the absolute value of u plus 1. Right? That's just a integral that we learned back in Cal 2, right? And then, of course, we can't forget our bounds, or else we'll be very confused. We'll go from 0 to 2a x naught. All right, now let's just plug in our bounds here. We'll have 1 over a, and then 1/2 times 2a x naught squared plus 1/2 log of 2a x naught plus 1. And then, of course, our 0, we're going to have, when we plug in 0 to 1/2 u squared, we just get 0. And then when we plug in 0 for u here, we're left with log of 1. And log of 1, of course, is just 0. So we have minus 0 here. So that's good news. All right, now let's go ahead and just tidy things up a bit. We'll have, let's see, we can go ahead and plug in our x, or let's do this first. We have 1/2, and then we're going to square this whole part here. We'll have 4a squared x naught squared plus 1/2 log of the absolute value of 2a x naught plus 1. All right, now let's plug in our x naught. So remember that our x naught is just equal to the square root of 2a minus 1 over a. So wherever we see x naught, we're going to plug in that right there. So we'll have 1 over a times 2, because it's 1/2 in the 4, that'll leave us with 2. 2a squared, x naught squared is going to be 2a minus 1 all over a plus 1/2 log of 2 times a times the square root of 2a minus 1 over a. Oh, wait, I made a mistake. Sorry, that should be a squared, right? We're squaring this whole thing here.
Yeah.
So we need an a squared there. Right, plus 1 absolute value. There we go. All right, whole bunch of symbols here. Let's just try to see if we can make this look a bit nicer. All right, auto saving, nice. Thank you. There we go. 1 over a. All right, these a squareds will cancel and we'll be left with 4. Wait. Yeah, 4a minus 2. And then this log function will be 1/2 log of 2 times the square root of 2a minus 1 plus 1. And then let's distribute the 1 over a that's sitting out front here. So we'll have 4 minus 2 over a plus 1 over 2 times a log of 2 times the square root of 2a minus 1 plus 1. Oh, there we go. Okay, so let's go ahead and take a very close look at what we have right now. So the first 2 terms here is exactly what we had earlier when we tried this and failed, when we just did the substitution with u. Now we have this extra logarithmic bit tagged onto the end. So what we remember, our original goal is to show that this whole expression right here is greater than 4 for some a, right? There exists some positive a that makes this expression here greater than 4. So we have to see if we can find such, see if that's even possible, right? So let's just rewrite this as equal to 4 plus 1 over 2a times the log of 2 times the square root of 2a minus 1 plus 1, and then we'll have a minus 4, right? And this 4 just came from the 1/2 over a, right? Because if you redistribute this over to the 4, you get 4 times 1 over 2a, and that's nothing more than 2 over a, right? So no trickery here. We've just put all of the bad terms right here, right? Because if we remember back, this negative term gave us quite a trouble when we were just substituting in u. So we want to chuck it over here with this logarithm and see if those two will sort of go away. Now, it would be very nice if we could show that the log of 2 times the square root of 2a minus 1 plus 1 is greater than 4, right? Because if this is true, that means that this whole thing here is positive, right? So if this is greater than 4, that means this whole term is positive. That means this whole entire expression is 4 plus a positive number, which of course is greater than 4, and our problem solved. And we're done. So all that's left is to prove this inequality here, to show that there exists an a that makes this true. So let's look at what we can actually do here. So this is true, right? This statement's true if and only if that this equivalent statement's true. 2 square root of 2a minus 1 plus 1 is greater than e to the 4, right? Because here all we've done is taken, we've exponentiated both sides by e, right? So this statement that we're trying to prove is only true if this statement's true. And then let's see if this statement's true, right? Here would have 2 square root of 2a minus 1 has to be greater than e to the 4th minus 1. Square root of 2a minus 1 would have to be greater than e to the 4th minus 1 over 2. Square both sides. 2a minus 1 has to be greater than e to the 4th minus 1 over 2 squared. So then we're left with 2a has to be greater than e to the 4th minus 1 squared over 4 plus 1. And then our final step, a just has to be greater than e to the 4th minus 1 squared over 8 plus 1/2. And of course, this is just some number, right? Some real positive number. And a can be any number so long as a is greater than 0. So all we have to do is choose a to be some number greater than this thing right here. So as long as a is greater than this little bit I've highlighted, then we have that this inequality holds. Therefore, we have that this is positive, right? So if we choose a, let me just take this right here, copy that. Oops. If I just take this, copy it, and let's move it down. Right, because we have that this, if you recall, this right here is equal to L, right? This was what our integral evaluated out to. And we know that this yellow bit is positive. So that means we have 4 plus a positive number. So that's greater than 4. So we have our L is greater than 4. And what is L? L is just, let's see, where was it? Yeah, right here. L is just exactly our arc length. Where do I have our L initially defined? Yeah, right here. L is just our arc length of the parabola. And we've just proven that so long as we choose a to be greater than that mess with the e to the 4th minus 1, right? As long as a is greater than that whole thing there, we have that this arc length is greater than 4, and that's exactly what the problem asked us to find. It asked us if we could find a parabola where its arc length inside of this circle is greater than 4, and we just did. And that's this whole problem here. So any a, as long as it's greater than this messy number right here, is greater than, its arc length is greater than 4 inside the circle. And that's it for this problem. It's done. Go ahead and finish it off, right?
Very nice, very nice. I have one comment to make though before you jump and solve the second problem. If you go back a bit to the estimate, the one with the radicals, right? You can also, so we said basically that the square root of 1 plus u squared greater than u is not good enough. Well, you can also, well, you can do it by hand, but you know, yeah, that estimate over there. And, you know, people might not guess, how did you come up with that? But you can also use the square root of x, let's say f of x equals square root of x, and you apply the mean value theorem on x plus 1 interval, and then you take x to be u squared, and then you derive a double inequality. In fact, the square root of u of 1 plus u squared is between u plus 1 over 2 times u plus 1 and less than u plus 1 over 2 times u, times u. So usually, okay, let me put it this way. Usually the square root of x plus 1 minus square root of x, so the consecutive, let's say, difference of the square roots is between 1 over 2 times square root of x plus 1 and less than 1 over 2 square root of x. It's just an application of the mean value theorem. And if you plug in x equals u squared, there you go. You get this double estimate, which one of them you have used it here. Anyway, but Also, if you don't, that's the easiest way. But if you want to be more try some fancy things, you can also employ the Taylor expansion theorem of this radical, and then you can just stop at the term that you like. You stop at the second one because you have u plus 1 over 2 times u plus 1, exactly, something like this. Anyway, that was the comment I wanted to make. Okay, Jack, let's go to the second problem.
All right, the second problem. All right, this was a bit of a long explanation.
That was good. It's not bad.
No, I mean like the problem. This next problem is just a lot that it asks in the beginning.
Ah, you mean the second? Oh, okay.
Yeah, a lot of writing in the beginning. All right. So this is again a Putnam problem. This one is from 2015. It's an A1. Right. I don't know if I said last time, but the other one's an A6. This is an A1. Let's see. So we're given 2 points. We have let A and B be points on the same branch of the hyperbola. Be points on the same.
Did you forget an I on points?
Oh, I just didn't dot it.
Ah, okay, yeah.
Hyperbola. Right, and all this means is when you do your hyperbola, you typically have 2 branches. This is just going to mean that A and B are on the same one. And our hyperbola in this case is just xy equals 1. Okay, so now suppose we have another point P. So suppose P is a point lying between A and B. On the same on the hyperbola. On the hyperbola. All right, such that the area of the triangle APB is as large as possible. Oh, so much writing and we haven't even gotten to the main problem yet. All right, just setting stuff up. Okay, so show that the region bounded by the hyperbola and the chord AP and the chord AP has the same area as the region bounded by the hyperbola and the chord PB, right? The same region bounded by the hyperbola and the chord PB. All right, so very first thing, let's draw a diagram of this whole thing because it's a lot of words, not a lot of pictures. So let's see here. Draw our axes first off, and let's do our hyperbola in blue. So that is a straight line. All right, here we go. So our hyperbola is going to look something like that, right? This is x times y equals 1. And then we have our points. Let's see, we could have A and our other point B. So we're given these 2 points. and we have to choose another point P also on the hyperbola such that the triangle between the 3 points is as large as possible. So just sort of eyeballing it, it's probably somewhere around here, right? So here's what the triangle would probably look like, right? So of course, this point here being point P. So point P is chosen so that this triangle right here has the maximum area given points A and B. All right, so what the problem wants us to show is that the chord AP and this hyperbola, let's see if I can draw this pink area here, right, between the hyperbola and this chord is the same as this area here. Can't really see it, but it's a little bit, right? So we have to show that these two pink areas are equal. That's what the problem's asking. So let's go ahead and try to maybe construct a map that will transform the plane to make these diagrams a bit nicer. So let's let alpha be anything greater than 0. And we're going to consider the map F, which equals the matrix alpha 0, 0, 1 over alpha. So why this map? It has a few nice properties that'll make this problem very easy that I'll get into. One of the, right off the bat, what you can see is the determinant of this matrix, the determinant of alpha 0, 0, 1 over alpha is just alpha times 1 over alpha, which is equal to 1, because remember, alpha is greater than 0. So, yeah. Our determinant's equal to 1. That means that this map is going to preserve the area, right? So if we have some sort of region in our plane and we apply this matrix map onto our plane, the resulting image of that region is going to have the same area as the original region, right? So if you take the region and the image of the region, they have the same area because the determinant of this matrix is 1. So that's one of the nice properties about this map that'll make this a good choice. So let's put some numbers in for these points. Let's let A, right, A be equal to the point A1, A2, and B equal to the point B1, B2. That way we can get some actual numbers and do some algebra with this. So let's look at f of A, and let's look at f of B. Or I should write it down here, f of B. Right. Okay, f of A. So f of A is nothing more than the matrix, right, times the point of A, which we said is A1, A2. So this right here, matrix multiplication, we have that this map will send A to alpha A1, A1 over alpha. And similarly for B, it'll send B, which we said was B1, B2, to, this sort of looks like an A. There we go. Sends it to alpha B1, B2 over alpha. Wait a second. This should be A2. Sorry about that. Yeah. All right. Now, we want to see what exactly these 2 points are, right? Because I've chosen this map in such a way that I'm hoping that the 2 points, A and B, get sent to something like this, right? So if this right here, the original drawing is that, this new one is going to be the image of the drawing after we apply our function. So this red line is just going to be y equals x, right? And drawing our hyperbola like that. We want that our new a, our f of a, say it gets sent here, and our f of b being sent here. Now, what's special about these 2 points, what we're trying to show, is that actually f of a is just the reflection of f of b across the line y equals x. And since this map preserves area, that means that when we draw our triangle, right? So just first off, trying to get the triangle, our point P is going to be this point here at 1, 1. Because since these 2 points, f of a and f of b, are reflected across the line y equals x, the point that will create the greatest area for the triangle has to be this point here along y equals x, which is just 1, 1. So we have this right here with this point being P. And then we have, again, our 2 pink areas, this one and this one. And then remember, since this map preserves area of regions, these 2 pink areas, this one right here, this region, this area here, has the same region as this one here. So if we let's call this one region 1. This region 1 has the same area as this region f of R1, right? And if we call this one R2, it has the same area as this one, which is f of R2. So since we have that R1 equals f of R1 and R2 equals f of R2, and we also know that f of R1 equals f of R2, that these 2 things are equal. Because these 2 points, f of a and f of b, are symmetric across this line right here, this diagonal. And that means that since this hyperbola is also symmetric across the diagonal, we have that these 2 areas in our image are equal. So we have that f of R1 equals f of R2, but because we know this map preserves area, we have these 2 equalities here from R1 to their images and R2 to its image. So we'll have that R1 equals R2, and the problem is done. So all we have to show is that our map here actually does what I've said it does, right? That it maps f of a to this point, that it maps a to f of a, and it maps b to f of b, such that they are reflected across this diagonal. So if that's true, we're done, right? So that's all we have to show, and that's what we're going to try to do right here with our two points, right? F of a and f of b. So how could we possibly show that these 2 things are actually reflections of each other? Well, if you think of them as vectors, right? Let's see if I can draw this. Let's choose another color. Let's choose this blue. Okay, so if you think of them as vectors, that's not a straight line. As vectors, we have this vector here for f of a and this one here for f of b. Now, if we add f of b to f of a, what we're going to get is a vector that lies on this diagonal right here. So we'll have some sort of vector, this big red vector, which is just some multiple of the vector 1, 1, all right? So if we can show that the image of A plus the image of B is just a multiple of 1, 1, we're done, right? Because that means that f of A is being sent to f of A and f of B. That means that they're reflected across our diagonal here. So all we have to do is show that. So let's go ahead and look at what we have here. So f of A plus f of B. So that would be, still straight lines. Need to change that. There we go. So f of a plus f of b. That is nothing more than alpha a1, a2 over alpha plus alpha b1, b2 over alpha. And that's just alpha a1 plus alpha b1, a2 over alpha plus b2 over alpha. All right, so we want to show that this vector right here is equal to sum k times the vector 1, 1, right? So if we can show that, we're done. So that means that we need to show that alpha a1 plus alpha b1 is equal to k times alpha minus 1, sorry, alpha times a squared, not a squared, a2 over alpha plus b2 over alpha, right? Because if this is just a multiple of this, that means that we can just, we're just a multiple of 1, 1. So let's see. Let's go ahead and take out alpha here, a1 plus b1. And here, let's take out a 1 over alpha. Let's keep that k there. We have a2 plus b2. So then multiplying both sides by alpha, we're left with alpha squared is a1 plus b1 equals k times a2 plus b2. And then we'll have alpha squared equals, let's see, k times a squared plus b squared over a1 plus b1. Let's move down a bit. Wait a second. Up, right. We took rid of that. So we have that alpha equals this square root here. So that means as long as, if we choose that, here if we choose alpha to be equal to, let's say, a2 plus b2 over a1 plus b1, we have that f of a plus f of b is equal to some, is a scalar multiple of 1, 1. And since this is a scalar multiple of 1, 1, we have that these two things are reflected across our original diagonal here, and all the regions, like I've said, become equal, and we have the solution.
Yep. Okay, nice. Very nice. Well, I was thinking of a bit different of solving this problem. This is a purely geometric solution. That was really nice. Wow, that's impressive. You know, usually when you have coordinates, for example, when you have 3 points in the plane, right? And you know the coordinates, you can compute the area of the triangle formed by just you know, there is a formula. If you 1/2 times some determinant, and then in this case, you can assume that all the 2 points of A and B are in the first quadrant. So you know the coordinates, they're like T1 and 1/T1 and T2 and 1/T2. And then when you have a point P, right, between that, then you'll have, let's say, P of coordinates T and 1/T, and then you just keep going. When you compute the area, you'll see that you'll get some function of T, and then you try to minimize that, and then you will have a minimizer. And then at some point, you'll know exactly how to compute the area of the two regions by just taking the integral, and then you'll see that that's exactly, they're equal. Anyway, but you did it like purely geometric. This is really, really nice. Wow, impressive. I see there are 2 people here. Do you guys have any questions? Nadia, Timothy?
No, Jack did a great job. It was nice to watch.
Yeah, anyway, this is recorded, so I will post the recording. Yeah. Anyway, there were two problems presented by Jack. Very nice. You find this on your own, right? Because it doesn't look. I don't think I have seen these solutions anywhere.
Yeah, I couldn't really think of a way to do it with integrals or anything, so I tried to come up with some sort of map that would make it nice.
Mm-hmm. This is brilliant. Very, very nice. Very nice. All right. Well, if there are no questions, then let me claim the host back. In fact, can I wait just a second? No, okay. All right. Well, guys, thank you for joining us. Jack, is there a way for you to send me the PDF file with these with these notes?
Yeah.
All right, that's great, because I can post this on my website, and also we have the recording. All right, guys, thank you very much. Let me stop the recording.